Everyone, and welcome to today's Tech Talk. With me, I have, as always, Ed Klotz, our senior mathematical optimization specialist. What a title he truly is, with decades of experience, and Richard Urbadik from our technical account management team. I'm Kostya, and today we will focus on model performance from the perspective of model formulation. So lots of things to go through, from weak to strong MIP models. Without further ado, Richard, why don't you kick it off?
Thanks, Kostya. And welcome everybody. It's been a long time, it feels like. So without further ado, let's jump in. This time we're gonna have a few slides and a few interactive elements as well. But as is almost customary at this point, we're gonna kick things off with a couple of questions. So, and this is really to gauge a little bit where the audience, where you guys are at when it comes to MIP formulation. So if someone says to you, a MIP formulation is weak, do you know what they mean? A, yes; B, kind of; C, nope; or C, or D, Jim. And I want to give a shout out to Ed here, who provided the visual representation for this particular question. So, Ed, Kostya, what do you think the breakdown is going to be?
Well, it's unfair because I can see the numbers. So over to Ed.
Okay, Ed.
To me, the question is how many people are going to say Jim. So I'm going to say 5% for Jim. Okay. I'm going to say, so that leaves 95%. I'm going to say 35 yes, 35 kind of, 25% nope, and 5% Jim.
Okay.
So,
wow. So about 80%, we're going 85%. Yeah.
Wait. Doesn't Richard have to weigh in, or can he see?
My opinion. So I think it's actually going to be less yes. So I think we're going to have around 10% yes, 40% kind of, and then the split, 40% nope, and then the rest Jim.
I'll end it right here because it looks a little different. Okay, so share the results. So 30 self-confident and say yes. What I know what a weak MIP formulation is. 45% are like kind of, nope, 20%. So that's good. And Jim, yeah, people don't fall for this. So Jim is only 3%, only more than a handful.
I have a feeling that's more of a troll.
We have a smart audience as always.
I was pretty close though.
Yeah.
Yes,
35, Ed, 35, 20, and 5.
Ed, you get the title. Okay, question number 2 though. Let's jump a little bit more into some technical question. So here we have a node log. And the question here is, for this node log, which I'm going to walk you through in a second, is which element do you think is the bigger bottleneck in this minimization problem? So here we're exploring some nodes. It goes down to 131 explored nodes. We have an incumbent solution. So we have a feasible solution already at the start, which then gets improved upon. And then we have a best bound, which doesn't move, or lower bound that doesn't move. And the gap obviously then decreases. And here you can see the iterations per node. So for this node log here, do you think the biggest bottleneck is the improvement of the incumbent, so of this guy, the improvement of the lower bound, so this guy, or do you think it's unclear?
All right. Phones are open.
And for this time, I'm not going to ask Ed or myself for the opinion, because I don't want to bias the audience just yet.
I think you already explained it quite nicely. Looking at the log.
Let's see. No, I mean, there's a lot of things happening in this small node log, to be very honest with you. So I would even go so far as to say there's no wrong answer on the screen.
All right, so we are at 82%. Wow, responses are still coming in. Can you believe it? We have hundreds of participants today. Wow.
Oh, cool. Wow. Hello, everybody.
Wow. Okay, so I'll end it here and we'll share the numbers. So 23% say the biggest bottleneck is the incumbent improvement. 55%, so we have a majority here, lower bound, and 22% unclear. So that is a nice point to start from when we talk about this topic. Definitely. Any comments?
Koski, what do you think?
Well, if I look at this log, and we look for bottlenecks in a log mean things are not progressing. And so what isn't progressing here? Well, we certainly explore nodes. We certainly improve. It's a minimization problem, so we certainly improve the best known solution. But the bound, boy, 2 seconds, 9 seconds, 100 seconds, nothing changes. So clearly the bound isn't moving at all. So the bottleneck is definitely the improvement of the bound.
Ed, what's your take on this?
Well, what makes it a bit unclear is it's always possible that there is a solution that meets the best bound. And we see that at the end, we get very close to it. We get down to 67. And, it looks to me like what's going on here is that there's an integer objective, that the objective function is all integer variables and all integer coefficients. So you can make an argument that there really was very little potential for the best bound to improve. But if you're going to force me to make a choice and say, no, you can't waffle, you got to pick one, I agree with Kostya. If I were looking to improve performance and try to get us to this solution of 67, in half as many nodes, I would be looking to try to understand why the best bound doesn't move. It's unclear, but with a bias towards lower bound improvement.
Yeah, I think so. I actually think it's unclear if one pretends to not know that this is an integer feasible. So it's the objective function can only adhere to integer values, and the reason is if you know that it only has integer values, the objective function, then exactly the situation that Ed says occurs. But if you assume that it doesn't, that's just some sort of slack variable in there or so on, then it's not completely clear. I mean, if I see this node log with all zeros and all the incumbents ever found, my guess would be immediately, okay, this is an integer objective function, or an objective function can only adhere to integer values, but it's not overly clear. I mean, also one other thing to note here, for example, the objective function values in the current nodes is always identical, right? So there's definitely also, I would assume, a lot of symmetry going on here, just because of this this situation. But yeah, I would agree with Ed. I would have picked probably unclear, but if you twist my arm, I would have probably said B, lower bound improvement, as did the majority of our audience. Interesting. So, okay, now that we're warmed up, our brain is loosened up, and we're ready to go. Let's switch gears a little bit. And you know what we just saw was, the lower bound wasn't moving, and then you might assume somebody just walking up to you on the street and saying, so why did the lower bound move so little? And then you could, put your academic hat on and say, well, it appears that the facet defining inequalities of the polytope defined by the convex hull, and I'm going to let you read the rest of this, you could make a very theoretical argument around why this does work or doesn't work, or why the bound doesn't move. But honestly, that's not what we do here at the Tech Talk. We don't want to give you some sort of theoretical treaty of this. If you want to do that, there's a ton of textbooks around this. So instead, you're not going to convince anybody with this. So I'm going to hand it over to Ed now, who, can show us a game around how all of this works. Ed, over to you.
All right. Thank you, Richard. Let me share my screen as soon as possible. Okay, looks like I can share now. Okay, let's see. Can I? All right, let's start with the game. So the game's visible now, right?
Yeah.
Yes.
Okay, so here's a little game. We've got a bunch of rectangles, and we have a score that consists of the area of the rectangle that surrounds all 6 of the rectangles in the game. And our goal is to reduce our score. So for example, you see that when I click on this one over on the left, on the right, excuse me, and move it in, the enclosing rectangle gets smaller, and I've reduced my score. So my goal is, of course, to make the score as small as possible. So we sort of look around and say, well, hey, this guy looks like he sort of fits in here. That looks kind of good. And you can see the rule is you're not allowed to have the rectangles overlap. So you hear that little beep every time you know, a rectangle bumps into another one and we have overlap. So we sort of say, okay, let's try this. Put this guy here. Let's actually move this guy down a little bit. Put this one here. Bring this guy, excuse me, there. And now we're going to slide this one over and there. So actually, that's not bad. I played it a few times. And if you get under 120,000, you're doing okay. And you can imagine, you know, you see a lot of white space still. So you can certainly imagine trying again and reorganizing things to get things smaller. Now, you might ask yourself, well, what's the best possible configuration? And we ask the all-knowing Gurobi polytope that question by clicking on it. And it solves that problem and gives us the optimal configuration. And we see that we were about 10% off. And then the other question is, well, what happens if you relax integrality and allow yourself to, in some sense, cheat? So when we relax integrality, what we're doing is we're saying, well, I'm going to be evil and just ignore the restrictions on overlap and allow myself to have the rectangles overlap. So we click on the Dr. Evil icon and we see the optimal configuration when we throw out or ignore or cheat on the rules. And what we see is then every rectangle, all 6 rectangles can be positioned to have the same coordinate for their upper left corner. So this relaxation solution is quite a bit less than either the solution we found or the one Gurobi found that is optimal. And you know, this raises a question. Now, you might say, well, yeah, the score of 75,000 is less, but it's not that much less. I've seen, you know, much worse MIP gaps. But think about this. Suppose we take one of these rectangles here and add 1,000 copies of them to the puzzle. Well, our MIP scores are going to go way up, but we can just lay all 1,000 of the additional rectangles right in here, and the relaxation score will not go up at all.
So maybe it's worth to say here that when we relax integrality, this is what happens under the hood in all branch and bound algorithms, which is the idea that you all the discrete choices are made continuous, and in this case, this means are the rectangles allowed to overlap or not?
Yes, in the sense that the only integer variables in this problem, really, as far as constraints go, are the ones that are used to ensure that overlap is forbidden. So that's the story with this game. It gives you a notion of a weak formulation in the sense that when you relax integrality, you get something that is disconnected from your actual MIP model. Now, you might say to yourself, well, this is just a game. You know, how does this relate to real world applications? So let me stop sharing that. And now I'm going to share something else. So bear with me for a second. So let me share where we left off. Okay, so now you should see the slide that we looked at. So we just showed the game. And now the question is, well, what's the application? Can you show me a real world application? And a good example is layout for chip design. So you basically have a bunch of rectangular objects that are different hardware components on a chip. You know, they have these connectors because they need to communicate memory and other things with various other components on the chip. And you want them to be as close as possible to each other to help speed up communication. So that's one example. You can view this essentially as the dual of the two-dimensional bin packing problem. And by that, I mean, in a regular bin packing problem, you have some number of bins available with fixed capacities that you want to put objects in. Here you have one bin, but the capacity is the objective you want to minimize. And it's a question of putting the objects in the bin in a way that keep the capacity at a minimum. And then, excuse me, there are other applications as well involving two-dimensional job scheduling, where say you have time and memory for assigning compute jobs to servers. So this type of scheduling model will either generate either this two-dimensional bin packing problem or its dual. And in both cases, the overlap issue that we illustrated with the game makes these MIP models potentially challenging. So with that, I'm going to stop sharing and let Richard move on with sort of a broader overview of what we just saw.
Yeah,
Okay.
Before I move on, another application, by the way, a real application is if you have a shop floor, so you're building a factory and you want to position machines. So you have multiple steps that you have to follow, and you have handovers from, like, you know, machine A to machine B to machine C. You want those distances often to be as small as possible, because you don't want to carry, for example, a heavy piece of machinery, you know, 200 meters in one direction. And so this is another example where this application or this model comes in, minimize the area where you position these machines. And then there's often some additional constraints, such as you have to have certain things close to each other, etc. But so there are a lot of, I mean, it's optimization in a way, right? Costa, can you think of any other example?
Well, in the general case is layout. Yeah, things need to be somewhere, and then you have something in between connections, and you're looking for a layout that works. I mean, probably many applications. I think I saw urban planning in the chat. Yeah, similar thing. So if you think of, you know, ways of aligning things. I mean, for cities, usually there's not much choice where to put the buildings. That's usually already there. But if you explore new areas, might be. So any sort of layout problem probably fits here.
Yeah. So sorry, go ahead.
Sorry to interrupt. I see a couple other interesting comments. Yeah, somebody pointed out cloth industry and steel industry. So I think steel industry relates to Kostya's comments. Somebody else commented that machines are not rectangular. And there's certainly some truth in that, but you can extend the modeling to shapes that are more complicated than rectangles, and you can still handle that. And the fundamental challenge of forbidding overlap remains the same, even if the shapes become more elaborate.
Yeah.
So with that, I yield back.
You have one other, just closing that off, you have one other, when you have rectangles, by the way, one thing we didn't look at is rotation.
Correct.
Right. So the question of, are they always oriented in the same way, or can you rotate them? So this is a question when you have those machines or other objects, do you have rotational symmetry, or do you have to account for that as well?
Right.
Okay.
And if you fiddle around with the game, one thing that quickly emerges, and I'm not going to go back and show it, is that if you had the ability to rotate, that would give you additional opportunities to get a better score.
Yeah. So now I think now it's pretty obvious from a visual perspective what weak means. A weak formulation is one where you can, let's put it in those way, in a only definition we're going to show today, I promise, and this is a very loose definition, is when the solution of the LP relaxation provides a bad bound that, and this is key, is not easily closed. So the idea here is when you have these overlapping rectangles, you might move one or two out of the way, but as Ed said, if you have 1,000 copies, you have to move all 1,000 out of the way. So you have to branch down 1,000 of these violation constraints in each dimension before you even get to a feasible solution, or to something that is closely resembling a feasible solution and closing that gap. So let's look at this in a slightly more detail on a theoretical level. So for those of you who are not maybe as familiar, so there's two main steps when it comes to solving MIPS from an algorithmic perspective. And I know I'm simplifying here a lot, so do bear with me for those who have a bit more experience. So in the beginning, you have an LP relaxation. And the idea behind the LP relaxation is you take all your discrete components and you make them continuous. You say, like, just throw all the discreteness out of the window. And then in the branch and bound part, you basically gradually walk through your discrete components and fix them. And that way you can think about it, if you fix all your discrete components, then you have a solution or if it's feasible, you have a solution to the problem. So what does that mean in terms of weakness? So yes, weakness has a theoretical basis. And if you're interested, you can read the long expose in a couple of slides back. By the way, you get all the slides in the game, everything. If you want, we'll send a link after the tech talk. But most importantly, it's a symptom. So when you read a log file and you see this non-moving lower bound and so on, then you're like, okay, we have to look at this formulation because clearly there's something not working. And the way to think about it is when you have a weak formulation, the tree search has to spend a lot of time trying to repair the LP relaxation solution such that makes it more palatable and more realistic scenario for the actual primal solution. And finally, and this is going back to Ed's game, the key here is that when you relax integrality, this gives you access to unrealistically favorable objective function values. So in this particular case that Ed said, you can shrink all your rectangles together such that they provide a value of 75,000 that is way off the original value or the optimal value, and this is only accessible due to the violation of the integrality. Ed.
Yeah. So the second and third thing are also somewhat connected here, because we get these unrealistically unfavorable or unrealistically favorable objective values. Not only does the tree search need to spend a lot of time and effort to repair the LP relaxation solution, but the information from that solution about how to do the repairing can be deceptive because of this unrealistic aspect in the third item. So with that, I lower my hand.
Yeah. So now we're gonna, I think we now spent like around 20 to 30 minutes talking about how terrible weaknesses and it's all bad, and you can have a lot of applications where your model's seemingly bad. So now let's put on our positivity hats and let's think, what is it that we can do practical things we can do to make our formulation be stronger. All right. So that's also why the title of the talk is Converting Weak to Strong MIP Formulations. But before we go there, Kostya, do we have any Q&A questions we wanna take right now?
Yeah, for me, maybe we can spend a minute or two. Well, we talked about weak. Of course, the natural question is, when do we say a MIP formulation is strong? I think that's an easy one. Ed, do you want to comment on that?
Yeah, it's strong when it's not weak. So let's go through and look at our three examples, our three items here on this slide. I want to focus in particular on the third one. So if relaxing integrality gives you, has sort of a realistic connection, if the relaxation model, if the physical system is reasonably well connected to the MIP model's physical system, then you're not in the bad situation of the weak formulation that we described here. And then the tree search has better information and has to spend a lot less effort to repair the LP relaxation solution. So you're going to get better results. And if you want to go onto the theoretical side, you can talk about the volumes of the convex hull of the integer points versus the volume of the relaxation region. And the other thing is, in terms of the solution process, you'll tend to see better progress in the lower bound of the Gurobi node log rather than a long sequence of LP relaxations, all with the same objective value.
So, Kostya, let me put a question back to you, though. So, would you call a model formulation weak if, yes, the original lower bound from the LP relaxation is bad, but the model is susceptible to, like, cutting planes, let's say, such that cutting planes provide a great benefit in terms of the lower bound? Would you still call that formulation weak, or would you just call the algorithms like saving you?
Well, that's difficult for a few reasons. So first of all, I mean, you can certainly mathematically, look at, solution spaces and see, the closer you get to the convex hull, then yeah, you could call this tight usually, or tighter. How much? Well, that's not clear. For me personally, weak or strong is a property of the runtime behavior. So as a practical definition, yeah. So it's not per se the formulation itself, but it's essentially what you observe when you try to solve it. Because even if we see a very, very not tight, weak, whatever relaxation, so if it's very, very far off at the beginning, if we apply the right techniques, if we can generate the right cutting space, this can be very, very easy to solve. So it's certainly, this comes to another question that we have here. It's so if you limit the formulation, if you limit the definition just to the formulation, yeah, then yeah, you can probably say something already at the beginning. But if you really want to see if that results in a performance problem, there's no other option than to solve it. So that's why we have kind of this vague definition. Yeah, we call it weak when we look at the initial bound, but to be honest, that may not even be interesting, because over time this can or cannot easily be fixed. So runtime behavior would be more my definition, but again, that's not a property of the formulation.
Yeah, I would say Gurobi already has a lot of built-in features to strengthen a formulation, but sometimes all those features are not enough. And that's the situation where we need to think about using our model knowledge in certain ways, which we're now about to go into in the rest of this tech talk.
Yeah. Awesome segue, Ed. So if it's okay with you, Kostya, I will go on a little bit and then we can take some more questions afterwards. So yeah. so now we're at the bottom of the motivational part. We have identified all the things that are bad. So now let's go up a little bit and see what we can do about it. So these are the three options we are going to cover today. This is not at all an exhaustive list. You can do a ton of other things, but these are the things that we thought are the most important to highlight and the most effective. So the first one is, you already heard us mention cutting planes and or cuts in short, and so some of you may not actually know what a cut is. So we're going to take a quick pause here, and I'm going to start sharing my other screen, which is, this is a game called the cutting plane game. And this was developed by a professor somewhere in South America, I believe. I forget the name. And this is the edition for combinatorial optimization at work 2020. And basically the idea here is, you have here, and let me zoom in a little bit. These dots represent the integer feasible solutions to your problem. And the dark gray area represents the feasible space. And you can see this gap between these dots and what's called the convex hull of the LP relaxation. This is the part where you can never actually have a solution. There's no way the solution is going to be on top, not on a dot. So what you can do is you can cut away that part of the feasible space without actually eliminating any feasible solution. And that's what's called a cut. And so on the right-hand side here, we have 4 of the most common cutting planes. So for example, we have Gurobi cuts. And if we apply this, come on. Why are you not? Okay, something is not. Because I wasn't sure which one I was picking. Okay. So you can apply these Gurobi cuts. And by applying these, you reduce the size of the feasible space that the LP relaxation has. And if you now see that we add, come on, okay, and then now I'm thinking I'm out of options here. I should have. Can I apply one more? Excellent. So now you see I was able to cut away all the, let's say, excess around the convex hull, or around the integer feasible points. And so you can now think that if you now have a solution to an LP relaxation that is going to be in one of the corners, by definition, it's going to be a solution, then it's going to be identical to the solution, to an actual feasible solution. And so that's great, right? So this is the best possible outcome. If the convex hull of the LP relaxation, so the area, the feasible space, and that of the actual MIP are the same. And if they're not the same, then the more looser it gets, the less tight, as Kasia put it, is the formulation. Okay, this was just a very brief. If you want to play this game, you just Google cutting plane game, and you will have a good time playing these games. So this is a very quick introduction of what a cutting plane is. And so now your next question may be, but doesn't Gurobi have cutting planes implemented? And so now I'm going to put Ed on the spot, since he's our resident senior mathematical optimization specialist. Do you want to answer this fine young gentleman asking, doesn't Gurobi already have cutting planes implemented?
Yeah, it does. And they are what I would call very generic, in the sense that they look for common structures that show up very frequently. And the next few slides will touch on this. And certainly when you see lack of progress in the lower bound, one of the things you want to first try before you take things into your own hands is to raise the intensity of Gurobi's cuts and see if that resolves your issue. But in many cases, your model has, very specialized types of constraints that are not generic enough for Gurobi to pick up what the right way to strengthen the formulation is. And that's what we want to focus on in the rest of the talk. What do you do when the more generic cutting planes in the literature aren't enough to get you the performance you need? And what do you do to make use of your own model knowledge to derive more customized cuts that can strengthen your formulation?
And Kostya, just to follow up, how often, like, because I mean, you've been in support for many, many years, how often do you see cutting planes, so the cut parameter from Gurobi making a difference versus actually implementing your own cuts or strengthening the formulation manually?
We do have quite a few power users who implement their own cutting planes. So it's definitely something to try for hard models. But it really depends on the problem type. So there are definitely problem types where, you know, manual generation of cutting planes, usually over time through callbacks, helps. From a support perspective, changing or adjusting the intensity of cut generation also makes sense in many cases. The problem is, you know, how much effort do you put into this? Because sometimes it takes you know, quite some effort to derive cutting planes, separate cutting planes. Sometimes it doesn't. Sometimes you can spend a lot of time in generating something that doesn't really pay off. So when we tune models, playing with these parameters is certainly something you can always try. We even have a few models where turning cutting plane generation off helps performance. So it's not that it's always helpful. What I'm trying to say is playing with it is worth a shot, especially in cases like something that we just saw, where the behavior of the bound isn't satisfying, so to say. So it's always worth to see, you know, turn it up, see what happens. If something improves, then it's a sign that you should try it. And it's not just the parameters for the cutting planes themselves. There are also indirect or meta parameters like MIP focus. I mean, if you shift the focus to, then internally, of course, it affects the cutting plane generation. So long story short, yeah, to play with it. It's certainly worth trying. Of course, the default values work well in many cases, but if I had to look at whatever the last 20 tuning tickets, changing some sort of cutting plane behavior was certainly, I don't know, 4 or 5 of them, maybe less. I you know, just guessing, but it's significant. Yeah.
Okay, so now let's look at 2 very concrete examples of what that means cutting plane wise. And so we're going to take very, very simple examples here. So this particular example, what we have here is we're maximizing, in this particular case, when we have 3 binary variables, x1, x2, x3. And then we have these 3 constraints. So these constraints say, well, either x1 or x2 is allowed to be 1, either x2 and x3 is allowed to be 1, or x1 and x3 is allowed to be 1. Right, so you sum these up, and these are, each one of this pair has to be less or equal than 1. And so now, if you look at this, you're like, okay, so what is so bad about this formulation? Well, the problem is that if you now relax integrality, so you don't assume this is binary, but this is a continuous variable bounded between 0 and 1, then actually x1 equal x2 equal x3 equals 0.5 is the optimal solution. And you can just substitute this in, you get an objective function value of 1.5. All great. The problem, though, is that this, you can already see, is actually not feasible for the integer part, right? And so what can you do about this? And the idea is, what happens if you combine the constraints? So you just sum them up, just linear algebra, just sum everything up, and you then get 2x1 plus 2x2 plus 2x3 less or equal than 3. And then what you do is you divide everything by 2, and then you find that the sum of 3 binary variables has to be less or equal than 3 halves. But if you think a little bit more, these on the left are all binaries. The right-hand side cannot be a fractional value. It will be either 1, 2, 3, or 4, or whatever. So actually, you can round down, and you can actually say x1 plus x2 plus x3 is less or equal than 1. And so you can see now you strengthen the formulation. Another argument for this is you can create what's called a conflict graph. So you can connect these, you can represent these constraint set as a graph and say at most one binary in this clique can be 1. So you connect it, you have a clique here, and then you can derive from this that the same exact cut. So there's two different ways to arrive at the same cut. And now you might say, well, so what? What does it give me? Well, if you now add this cut to the formulation up here and substitute in the values, you 0.5 plus 0.5 plus 0.5, that's 1.5, less or equal than 1. That's infeasible, right? In fact, this is the objective function value, and this is less or equal than 1. And so you will actually see that the objective function value, so the LP relaxation objective function is the same as the optimal objective function, right? So you can see that both of these arguments result in what's called a cutting plane that helps you strengthen your model. But I always hate it when people provide this type of math on the slides because it makes it very difficult to follow. So what we're going to do is I'm going to show you a little bit of a different representation of this thing. So this is, if you can see this now, this on the left hand side, you can see this is the model we're solving. So this is the exact same thing. And here you can see already added the cutting plane we have. Now, if you see this this red kind of triangle or what is this, pyramid, you can see this is the integer feasible space. So this is the convex hull of the integer feasible space. And then this light yellow part, this is includes also the feasible space of the LP relaxation without the cut. And you can see all of this yellow part, all of this is feasible for the LP relaxation in the beginning. So if we don't add the cut, and you can see when you go around here, all of this cut, and then the cut that we add is exactly across this line, across this plane, three-dimensional plane, and cuts off all of this yellow part, right? And so that's really where we're gaining performance, or we're getting a tighter lower bound, because we cut away all of this quote-unquote unnecessary space. Kostya, do you have any other comments around this?
No. I think that's a very nice visualization.
Okay. So this is the first type of cut we quickly wanted to show you. This, by the way, these two cutting mechanisms that we showed here, this is called on the left hand side is a mixed integer rounding cut. So if you in a Gurobi log see MIR, we also have a parameter for this. This is what that means. And the right hand side, this is called a clique cut. So the next cut to talk about, and this is I swear I'm going to stop monologuing in a minute after this slide, is something called a disjunction. And this disjunction cut is quite important to understand because it's not completely trivial. So let's think here we have a different model. We have x plus y. So we have two continuous variables here, and they're bounded between 0 and 5. All good. But then we say, you know what? The absolute value of their difference has to be greater or equal than 1, right? And so if I tell you this, then what can we deduce from this? Well, if we then substitute, again, x minus 1, the absolute value, that means that x minus 1 has to be greater or equal to 1, or y minus x has to be greater or equal than 1, which means that if we, again, substitute this, we put y on the other side and have y equals 0, which is the lower bound. That's x greater or equal than 1, or y greater or equal than 1. This is the what you can derive algebraically. And then you can, again, add these things up. You get to x plus y greater or equal than 1. So you can add this particular cut by resolving basically this disjunction, this if else kind of thing. But then again, the question comes, you have to ask this question with cuts, like, are they trivial? Are they redundant? Do they add anything? Well, the thing here is, and I appreciate that this might be a lot to take in on a Tuesday morning or evening, depending where you are in the world. So you will have those slides and can look at it again, and please feel free to send us questions if you have. If you take this model on the left, and actually what happens under the hood is we create a binary variable called Z. And this binary variable adds this indicator constraint, which is basically this constraint, the x minus y, will be active if the x is 0, and in the other one will be active if the z is equal to 1, right? So if the z is equal to 0, then it's x minus 1 greater or equal 1. If z equals to 1, then y minus x will be greater or equal than 1. And so now if we add this cut, the LP relaxation of this guy is x plus y is going to be cut off, because if we don't have any cut, it's going to be x equal 0. Now, most of you will feel like this poor guy in the beginning, where it's a big monologue about integer feasible halts. So again, let's look at this from a visualization perspective, because that's going to give you more of an understanding of what's happening here. So again, we're going to look at the model that's up here on the top left of the screen. So what's happening? This is the model. Great. So what? What you see here, the gray area, is the feasible region. So the red part is what's cut off. This is when z is either 1 or 0. This red part is cut off. And so what happens when the integrality is relaxed? Well, z can be anything, truly. And so if we take this off, all of this is the feasible space. And you can imagine the LP relaxation then is somewhere down here, 0, 0. But then what happens if we add our cuts? So the cut we just mentioned, let me just zoom in a little bit. We can actually have a symmetrical cut on the other side as well. You can see that now we adjusted the convex hull of the underlying LP relaxation. And because of doing this, because we made the convex hull smaller, this LP relaxation we had down here is no longer feasible. And so we actually strengthened the formulation. We created a better value for objective function value for the solution of the LP relaxation. Ed, Kostya, I want to take a sip of water. So what do you have to add here?
You want me to go first?
Yes, Ed, you're put on the spot.
Okay. Yeah. I think the main thing is this is very similar to the issue with the overlap that we discussed before, how this is similar to a non-overlap condition, that the distance between the, say, horizontal coordinates of two rectangles has to be at least 1. So it's trying to address some of the challenges we have there before. Go back to the sort of the first picture you had, if you can. Yeah, actually, the second one was even the one that shows everything, that shows the cuts and the, yeah. So here you have the blue is the feasible region for the MIP. And then you basically take the convex hull of the two blue regions to give you the purple line that actually gives you the cut, that cuts things off. And if you look in a textbook for the underlying way these cuts work, that's essentially how the cut is derived. So that's all I have to say about this.
Gotcha.
Yeah, not much to add. We have a few questions, so looking at the time, we should probably move on.
Let's take one question. It's okay.
So one is easy. And I'm not sure if I get the question right. What is the name of the convex hull / disjunction maps made? Maybe this is about the package that you used, Richard, to draw these pictures.
This is just Plotly. I just built this myself.
Okay, so that's Plotly. All of them, right? That we saw. Yeah. Plotly as a Python package.
Yeah. So all of this is, these are handmade for this talk, anyways.
Yeah. Well, I have not sure if now is the right time, but here's an interesting question. I think it fits. Can we detect a weak formulation if the solution deviates when we turn off pre-solve? I'm not sure what deviates mean, but So, but anybody wants to take it?
Well, if he's talking about the LP relaxation solution changes dramatic, if it degrades when you turn off pre-solve, that is in some sense a sign that the initial formulation had weakness, but on the other hand, there is at least some indication that Gurobi sort of did some pre-processing that strengthened it, so that maybe it's not a concern, and you still need to look at what happens after pre-solve and the rest of the optimization begins.
I mean, this, I'm not completely sure, but does pre-solve, do we apply cuts in the pre-solve phase? I don't think so.
That's a hard question. We don't apply the cuts in the cut parameters, but at the same time, there are certain simple bound strengthening and probing operations
that's
that
a cut.
Inherently are cuts. So it's a question of semantics there.
That's true. Yeah. Okay. In the interest of time, so we don't have much more to go through, because the biggest part really when you have these weak formulations is cutting planes in whatever shape or form. And I hope we have shown you that this is really the way to go. But there's two more elements that we quickly want to touch upon. The first one is, and already this came up, if this is a weak model, what is a strong model? So here's the classic, which is called the cutting stock model. And basically you have to imagine you have here, you have boxes, you have certain patterns you want to cut. So let's imagine you have like a big piece of slab of wood and you want to cut certain elements from it. And you want to say 22 times, I want to have something that's 13.8 meters long, 25 times, and so on and so forth. And then you have certain, let's say, slabs of wood or whatever paper. It's all it has applications in a wide variety of things. And this model is this is called the cutting stock model. And the idea here is you want to minimize the number of these master rolls, as they're called, you use. So this Y. So Y1 is you use master one, Y2 is you use second one, and so on. And you have to cut each of the patterns. You have to satisfy demand, but you cannot exceed the length C of your master roll, right? So this is a fairly common model. And then here's some annotation of this. Each element assigned to one master roll capacity if used. Now, the thing here is, if we now look at this from oops, did I just stop sharing? That was not the point. If we now look at the LP relaxation of this, the LP relaxation here is you can actually just assign fractional values of these elements. So you can assume this is not just 13.8, but this is actually much less. And so you can see that you can now say, oh, wait, you know what? I can actually copy this element and copy this element here and add it here as well to improve my formulation. So you can see you can get an unnaturally high objective function or low objective function value simply by ignoring integrality, right? And so this formulation is classically a classical weak formulation of this particular problem. So what can you do to make it strong? Well, the thing is, here we ask which element goes into which bucket. That's the fundamental question. But you can actually pre-compute all possible what's called cut patterns. So, for example, what is the pattern that all elements fit into one row? All elements blue, then 2 red, 1 blue, and so on and so forth. You can generate all these possibilities, eliminate all the symmetrical ones, and then you are left with this problem on the right. And this problem on the right has a much stronger formulation, because you can't just, you no longer talk about individual elements, but you only talk about cut patterns. And by doing this switch, by changing the logic of how you think about the model, from thinking about, okay, elements go into buckets, to pre-computing all of that choice and just saying which cut pattern do I apply, your model becomes much stronger. And we can actually see this in the log file. So the left here, this is a log file for the original problem. And you can see it takes 4 seconds, but the time of this is all tiny anyways. But you can see we spend quite a lot of time here strengthening this, whereas the log file for for the right-hand side formulation, this solves in 0 seconds. But more importantly, you can see, look at the best bound. This is 72.9. This, okay, I appreciate this is not a big difference, but you can, it should give you a sense of what's possible when you find a better formulation for your model. So, Ed, I have a feeling you want to say something. Yeah, I knew it. Go ahead, Ed.
Yes, just that there's another benefit besides the relatively modest change in the best bound, which is compare the number of integer infeasibilities at the root node. It's way better with the tighter formulation, and I'm speculating, but it certainly looks like that's the reason why the heuristics are successful at the root node with the stronger formulation, whereas you have to do a lot of branching to basically repair all the integer infeasibilities in the weaker formulation, and that's why the weaker formulation takes longer.
Yeah.
So with that, I lower my hand.
And then I know we're running almost out of time, but the last option I quickly want to mention, because we can't talk about strengthening, about weak formulation without mentioning some sort of decomposition. So this is the cutting stop model we just showed you, but even that formulation is, if you scale this, is going to be terrible. And the reason this formulation is going to be terrible is because your number of patterns that you have to generate is just awfully large. And so what happens if, pay attention to this right here. Instead of thinking of these as integers, saying I have to select 1, 2, 3, 4 cut patterns, we do the LP relaxation work for it and say, you know what, we're just going to relax integrality. But what's important here, we only use a subset of the cut patterns. So we change the way we solve it. We don't just write one MIP, give it to Gurobi and say, have fun. We actually select certain cut patterns before, and then we do something called column generation. So we generate new cut patterns to be added by solving a subproblem. Now, I will not go to the detail because column generation deserves its own set of tech talks almost, because it's a huge, huge topic. But the idea here is, if you can't add any more cuts, and if you can't change your formulation, then you might have to change the algorithm, and you might have to use quite sophisticated ways of approaching solving a problem if it is not possible otherwise. The idea here is you use the duals of the master problem to generate subproblem and then solve, and this generates new cut patterns that provide you a better objective function. Again, we should not go into more detail here. It's just a mention of it because it deserves to be included in this element. Ed.
Yeah, just one thing that despite the seeming complexity, Gurobi's APIs are really well suited to implementing this, and it really is surprising how easy it is. And as somebody who's been around since dinosaurs ruled the earth, the difference here between how it is to write a column generation application now versus 30, 40 years ago is really stunning. So with that, I lower my hand.
And in fact, I wanted to highlight this. Good that you mentioned this, Ed. I want to give a shout out to an open source contributor. So you can look, if you go on this link on GitHub, this is no affiliation with Gurobi whatsoever. I believe this was probably a student project. But when I was researching this talk, I found this, and I really wanted to say, like, this is not complicated. Go to this GitHub, check out this column generation approach for this cutting stock model, and it's really well done, in my opinion. So with that, let's quickly wrap it up with takeaways. What does it mean to have a weak model, a weak MIP formulation? Well, it means that the dual moves slowly, and the most important thing really is why. What is happening? What is going on under the hood? You have to compare the physical systems associated with the MIP and its LP relaxation. If there's a bigger difference, if there are big disconnects, then this implies weak formulation. Consider algebraic or geometric interpretations, especially for the cuts you saw. We can have an algebraic derivation I prefer geometric interpretations, but that's up to each one of you. And then there are several ways to address the situation: cutting planes, modeling, changing the algorithm. It depends really what works. I would go always in this order because it's from easiest effort first.
All right.
Take care.
Thank you all. See you next round.
Everybody.
Goodbye.
Thank you so much for attending.